Alrighty. An ideal nuclear power plant can be modeled as a heat engine that operates between a hot temperature of 612 Celsius to a cold temperature of 349 Celsius. Calculate the Carnot efficiency of the nuclear power plant. I am sorry, I cannot do that. Okay, so what is the formula for Carnot? Is 1 minus T cool over TH, right? Don't forget to turn these into kelvins. Turn them into kelvins. Okay, you'll get something between 0.2 and 0.3, or 20% or 30%. Okay, somewhere between that is the correct answer. All right, so the next page it says, explain with a reason why a nuclear power plant operating between the stated temperatures cannot reach that efficiency. And the answer is that, of course, a Carnot cycle uses isothermal processes and adiabatic processes. Although adiabatic are possible, isothermal processes take an infinite amount of time, right? So talk about that, right? Okay, so then we've got one of these branch problems, right? So the power plant works at 71% of your Carnot efficiency. So the answer that you got for A, that answer that's between 20 and 30%, okay, multiply by 0.71 and you'll get something that's closer to 20%. Okay, use the exact value because they are using 3 sig figs here, right? And then you can use the branch ratios, right? That the QH over 1 is the work divided by, and this will be your actual efficiency, right? Work divided by the actual efficiency equals QC over 1 minus that, okay? And what they're telling you is that the work is 1.33 gigawatts, right? This number is going to go here and here, right? And QC is what you're solving for. You've done these before, you can do it. Only notice that it's this is gigawatts, that's going to be joules per second. At the end, when you get QC, it'll be still in gigawatts, right? Multiply by 3,600, and then you'll get joules, okay? Because we're doing, what is it? Power times time is energy, right? Power is work divided by time, so therefore work is power times time. So don't forget that, right? And then it's got part D here, you know. Discuss the production of waste heat by the power plant with a reference to the first and second law of thermodynamics, right? This gets highly hypothetical, right? But the first law is that energy is conserved. So first law arguments are things like when the heat flows in, that either causes the internal energy to increase, right? Or it causes work to be done. This is a first law type thing. So you can talk about that. That's definitely first law, right? And then the second law has to do with entropy, is the notion that, and we can actually use the third law here, right? That absolute zero is impossible. They don't ask for that, right? The second law, though, says that entropy has to increase in the world, right? So you can say that not 100% of the energy that goes in, right, cannot be turned into work because that's a decrease. Heat is very random, work is very orderly, right? So you can't get 100% of this to turn into this. If heat is flowing in and it's not going to work, then it's being wasted, right? Remember the sand key diagram? We've got the high temperature, right? And we've got the branch that becomes work. Well, if you can't be 100% efficient, which you can't because the second law says that some heat is wasted, right? Then you definitely have to produce waste heat, right? Unless it's 100% efficient, right? So anyway, talk about that. You could talk about the sand key diagram. When you look at the mark scheme, it's very vague. It's got lots of options. I think it's got 1, 2, 3, 4. It's got 4 different things on there. But then it also says, or words to that effect, right? You gotta love that, right? Okay, so, BS it up, right? Remember, first law is just energy in equals energy out. Second law is the notion that you can't turn all of a certain amount of heat into a certain amount of work, okay?